We're going to get into the moon today. Hopefully we'll get into Mercury at the end of the week, and then we'll get into Mars and Venus next week, and then Jupiter and Saturn after that, and then our big ice giants after that. But how did we get here? We've been talking about Earth. So what did we talk about last week? Yes, up front.
Magnetism a lot. I know the beginning of the last class started with you drew like a hydrogen chain and then showed how the energy goes through that.
Yeah, yeah. I was talking about I was kind of modeling electricity as the surface motion of the atoms themselves, which I think is a pretty cool way of thinking about it. Um, Sarah, do you have something?
Yeah, it's just talk about how we were going into the technicalities of the solar wind and
Mm.
the sphere origins as well.
Yeah, the solar wind. That's a weird one. What do you remember about the solar wind?
Basically, that they kind of form like strings and snap off from like the sun's
Pole?
atmosphere.
Yeah.
Goes out towards us.
Yeah, yeah. It's I mean, that's more of a topic for next semester, unfortunately. But yeah, we had to mention it because, of course, uh, well, part of what makes this an awesome place to live is that we have that nice magnetic presence that keeps all that nasty stuff away from us. So it's worth at least thinking about how intense that radiation is and how fast moving those atoms are flying off of the sun. They're pretty gnarly. So what else?
Sorry.
Come on, guys. Yeah.
We're discussing the Earth's atmosphere.
Yeah.
Starting to get into weather stuff.
A little bit, yeah. Oh, I didn't even get to finish, and honestly, I didn't make plans to finish with that. Gosh. Yeah, I just realized when I was looking at things, this is the 7th week of this course. We have 11 weeks, technically. I think the last week's only one class, though, if I'm not mistaken. Might be two, but I think it's only one. So we are like 2/3 through this course, which means we have to get onto these other planets. So I didn't really get to finish with the atmosphere. What did we get to talk about? We talked about some pressure things. We talked a little bit about weather. Um, there's one piece of that puzzle I didn't get to. Maybe we'll get to it because electrical phenomena are really important in the atmospheres of some of the other planets. So same process. Maybe we can talk about it when we get to Jupiter or Neptune or something like that. Saturn. What do you remember about the atmosphere? Anybody interesting? Anything? You guys are so sleepy today. Come on, help me out. I'm gonna fall asleep up here. Come on. Somebody must have remembered something. Yes. Wait, hold on one sec, sir. Height, pressure, altitude. Yeah, that was kind of interesting, right? The units of we looked at this map of the atmosphere that I showed you guys called earth.nullschool.net. I was actually just checking it out before I came over here because we got crazy weather patterns going on. But it's interesting, yeah, they measure the height off the surface in terms of pressure, right? And you guys remember why that is? Why is it? What's the relationship between pressure and altitude? Is there more pressure on the ground or less?
There's less air above you.
Yeah,
Higher up you go.
that's right. Yeah, so it's cool. So airplanes can use that to estimate their altitude. It's a pretty reliable relationship. All right. Anything else that was interesting? Loose ends?
Must have been a boring class.
I know. Good Lord. Yeah, not good. Um, yeah. Well, the unfortunate part is, like, the further that we get away from our own Earth, the less we know, of course, about all of these things. So I'm going to talk about the moon today. We know a fair amount about the moon, but we also know very little about the moon compared to the Earth. So yeah, we're going to get into the realm of more questions than answers pretty soon. And so that's maybe harder for people to put into bins in their head as far as all of that goes. Any like general questions about anything we've talked about in this course so far? I'd really love to hear from you guys. This is really disturbing to just see these like half asleep faces out here. Yeah, come on, guys. This side of the room, something from you guys. What's interesting? Is there anything in the world that's interesting about this class to you so far? Yeah, hit me. Yeah,
Like satellites and telescopes up in
Mm.
space?
that's a good question.
Or do they get affected by it?
Yeah, generally speaking, most of the satellites are inside of that magnetic bubble that we have, so they're pretty well protected. But it is an interesting concern. You know, we're going to talk about the moon today, and obviously we haven't. Well, maybe it's not so obvious to you. People are trying to get back to the moon. So the story goes that we went to the moon back in the late 1960s. The Americans did. And they haven't put people back there since then, pretty much since the 70s. And one of the challenges right now is this radiation question, because you have to go outside of that protective magnetic space. And so one of the troubles with engineering these capsules to take people out to the moon is how you protect them from all of this nasty solar wind. There's other elements of radiation too, just from different cosmic sources. But yeah, it's a real concern. It's a real concern. I had a friend who worked at a private aerospace company, and they were trying to design modules, perhaps to take humans really far, like to Mars or something. And she was saying that one of the best barriers for radiation is actually water, and actually human waste works really, really well. So if you pump the septic stuff into the walls of the spaceship, you might be able to shield some of the radiation. So it's kind of interesting. I don't know. It is kind of weird though. Yeah. I was just listening to a podcast today talking about this new attempt to go back to the moon, and yeah, the radiation barrier is actually quite significant. Um,
There were missions planned, though, I thought. Didn't you have, like, the Artemis?
the Artemis project. Yeah. I don't know that we're gonna have a ton of time to talk about that. They did run the first version of that, which is the Orion module. It was an uncrewed version where they basically put some dummies in there. They tested them for radiation levels and ran this circuit around the moon. I think they orbited 3 times in retrograde, and um, yeah, they have another one. Of course, like most of these missions these days, gets backed up and backed up. They were supposed to have already sent the crewed mission by now.
Yeah.
It didn't happen yet. I think it's
It's
just
supposed to happen.
it's supposed to happen. It's always like right around the corner. So maybe.
The original slated, I thought.
Oh,
5.
yeah, 25. Yeah, I think it was originally like 20. It might have even been 24, but yeah.
It was 2024, then it was 25, then it was 26, and now they're saying it's not going to happen until maybe 2030 if they're lucky.
Really?
Yeah,
Well,
because NASA's already, I mean, they were already defunded before, but now they have no money.
yeah.
Especially since the government shut down, but also because the government administration wants all of NASA's resources to go toward nuclear weapon testing instead of what they're currently doing.
Yeah, well, it's quite interesting. So a lot of this rocket program, I'm going to not get too derailed about this, but when NASA was, started up, they were basically just using missiles. They're basically just, practicing putting people on top of these already established platforms. Um, and a lot of that early technology was developed by the Nazis during World War II. They had the first rockets, basically. So we rounded up all their scientists and took them back here and made them work for us on our missile program. And then eventually our missile program some arm of it turned into NASA. And we started trying to put people up there when the Soviets were beating us to it. So actually, the Soviets did most of the early space exploration. They had, all the firsts pretty much, and then the U.S. administration started getting worried, and so they were like, "We should catch up on this." But yeah, it's kind of interesting. The moon is, just to preface our discussion about the moon. It makes a kind of ideal place to practice everything that you need to be able to do in the long run, right? So, this is a beautiful place. I'm sure none of us really want to go anywhere else, but it would be nice, as like the same way that you might back up your computer, to have humans spread out over more than one place in the solar system, right? And the moons are really relatively close by, easy place to work with. It has no atmosphere, so it's not that hard to access and, you know, do work on, get up and down from. It's a pretty useful place to go to, actually, if you're interested in becoming a multi-planetary civilization, which is probably a good idea, like I said, just for backup hard drive reasons. Um, you know, the Earth suffers a catastrophic blow. You know, there's a nuclear bomb-sized explosion on Earth from an impact every single year. It's just usually somewhere where people aren't at. It's usually high in the atmosphere, so it's not that big of a deal. But we're getting hit with stuff all the time. We've been hit several times with enormous things before. I didn't have time to get into this in the course. Maybe we'll come back to it, but you know, the thing that took out the dinosaurs was what, like 100 kilometers wide? I mean, it was huge. It's like big, very, very big. Um, so that happens periodically. There've been, you know, there's been, I don't know, 5 or 6 mass extinctions on Earth where most of the species living just died suddenly as a result of something like this. So it makes a lot of sense to get off the planet, and the moon's a really good practice place for that. So I hope they do get back there. But you
I
know,
hope they get there so we can just recreate the hammer feather thing in 4K.
yeah, yeah, the hammer feather is really interesting. I will not talk about that right now, or I'll get lost. But yes, that will be really cool. So we'll see how far we get into our discussion of the moon. Today I want to talk about there's a few things that we absolutely can't skip because you can't take an astronomy course without understanding the phases of the moon. So I want to make sure you don't have any questions about that. It was in the textbook. All of these were eclipses. You should probably understand how that works. And then the history, for lack of a better word, the geologic history of the Earth, even though that's probably not quite the right word to use, but something about its natural history. Where did it come from? What's been going on? Which I think the closer we look at it, it will actually open up more mysteries than answers. But it's worth looking at the way that story's evolved. So let's just get right into it. You guys don't have any more questions about anything? Thoughts? Concerns? Yeah, please.
Uh, this is like kind of a little bit like off topic, but it was in your last lecture.
Yeah.
You were talking about how Earth, like maybe had a super like atmosphere in the past, and then and it was like possibly expanding, and how that ties into tectonic plates and magnetic pole flips. With the ocean floor being so young and like the poles wandering, I was wondering how scientists actually choose between like the normal plate tectonics, the explanation of that, and then like the possible explanation for expansion model. And then like what kind of future evidence would help prove one of them?
It's a lot to answer right there. So the decompressing planets is a model we're going to keep running into. I think that the more that we look at I don't know a better word than geological history. Geo means Earth, so the geologic history of another planet is not quite the right word, but I don't know a better way. You know what I mean? The natural history of these bodies. I think what I'm going to do is, as we look at each one of these bodies, I'll present to you kind of the story as we've understood it over the last few hundred years, where most modern scientists are at with it. And then I'll probably poke a bunch of holes in their contemporary picture of it. And I think really the alternative is something that's very metamorphic. I was actually explaining this to Andrew in an email earlier because he also wrote and said he was quite.
Ask the question.
What's that?
Pay her to ask.
Yeah, you basically asked the question Andrew emailed me about. You know, and as opposed to just standing here and just talking about it forever, I think we'll just keep seeing it come up because, you know, the alternative to many of the stories, including the moon story, which we'll hopefully make it to by the end of class today, the alternative is something that is really radical. It's only radical in so much as the timelines required for it are astronomical compared to what we're permitted by standard cosmology. But in its individual details, it actually makes a lot of sense. And if you read individual pieces of the puzzle, right, there's a lot of literature coming out in planetary science about how planets are changing, right, about how giant planets are losing their atmospheres really quick sometimes, about how Neptunes can turn into Earth-like planets, right? Like in its pieces, there's a lot of evidence for it. The last piece of the puzzle that you mentioned is this word proof, which is a really, really terrible word, actually. So the word proof actually comes from mathematics or from logic. It essentially means that given some set of assumptions, if you do sort of logical deductions based on some assumptions, I assume that, God, trying to think of a good example without, I'm not going to make an example, but if you process your assumptions correctly, then you can prove something mathematically. Generally, your assumptions are quite simple in mathematics, right? You have some set of identities that you assume, A equals A, A does not equal B, like some very simple things. With science, it gets a little weird because the assumptions include what you make of the evidence that you're collecting. So, I could introduce some evidence where I say, well, let's assume that the Earth is 4 billion years old. Now I'm going to prove to you a story. I'm going to give you a story of how the Earth came to look that it did in 4 billion years. But what if I'm wrong about it being 4 billion years old? Why do you think that it's 4 billion years old? Well, we tested the age using this radiometric dating of the rocks. Well, how does that work? Okay, well, you go and look at how it works. And, well, it really just tells you the last time these rocks melted. Well, we think that they're the oldest things that we found that were melted. It's like, so they're from the beginning of the solar system. It's like, maybe. Or maybe not. Maybe they just got completely cooked 4.5 billion years ago, as did a bunch of everything else, So, I don't know, the assumptions are really, really integral to anything that you conclude in science, in natural history. And it's different than mathematics because the assumptions are subject to change. So I really hesitate to ever use the word something has been proven with in this kind of process that we call science. It's more like, have you made a story that is logically consistent or not? And once you have, I'll hear anybody out. Like, you can give me a theory of whatever, and I'll listen to it. And the first thing you're going to have to ask is, like, does this make sense? Does it go from the assumptions to A to B to C? Okay, your conclusions follow from your assumptions. Then you got to go back to the assumptions and say, do these assumptions make sense? And that's usually where things start to fall apart. Or maybe the assumptions are compelling to you, and that's a theory that you might, put your money on. But the assumptions are always subject to change. We can always learn new stuff. So, with respect to the metamorphosing planets, anytime that we see this with telescopes on other solar systems, it's generally under these really black swan situations, like the planet's orbit changed and it ended up really close to the sun, so its atmosphere is cooking off really, really fast. These really like cataclysmic almost events that are really hard for us to look at our own natural history and conclude with any certainty whether or not any of these things happened. I think that you'll see that the more we start to look at our solar system, the more you'll see how, use like a smaller word, how diverse and weird it is. Like, the planets are weird, they're tilted at different angles. Some of them are spinning the wrong Venus is going the wrong direction. Like, it's a bit of a hodgepodge. It doesn't have that flavor of something that all sort of just is how it's always been. So anyways, we'll keep playing with this because I think it really is the alternative to a lot of this uniformitarian steady state business that we inherited from Laplace and Kant back in the 1700s. We've basically had the same model for where the solar system came for the last 300 years. And I think it's wearing thin a little bit. Last thing I'll say is that, again, the reason that a lot of these ideas, I think, aren't seriously entertained by, academic astronomers is because of the cosmological constraints. So the cosmologists have a theory called the Big Bang Theory that we don't deal with in this class. We deal with it next semester. But it basically tells everybody that they only have 14 billion years to make everything happen in, right? Not even 14 billion years, 13.8. That's a really, really short amount of time. I know it seems like a long time. It's really, really short. And so, in order to pull off some of these metamorphic processes, I would imagine you would need hundreds of billions of years, maybe thousands, trillions of years, thousands of billions. And so, if we are constrained by the fact that we believe that this entire state of existence is only like a dozen billion years old or so, that doesn't give us much time to work with. However, if that model disappears, then we're back in the same place people were at prior to the 20th century, where they didn't really have a birthday for the universe. And so the sea of possibilities was much, much greater. So, all right, thoughts?
I just remember you talking about, I don't know if it was in one of the podcasts that I watched or if it was actually in a class, but you mentioned that one of the most fundamental assumptions that we have is this idea of mass, and that we don't really understand it. We have a description for how it behaves, but we don't know what it is,
Right?
what all these different interactions, what causes all these different interactions with mass going on.
Yeah. I mean, I think, yeah, well, mass is, that word's been blown out, but it originally was a gravitational inertial concept. Relate that to the planets for me.
You were talking about how uh, a lot of the things that we're learning predicated on certain assumptions and
Oh, yeah, yeah, yeah.
all that stuff. And we don't even, that's like one of the fundamental pieces doesn't quite make sense or fit when you uh, dive really deep into it, I guess.
Yeah, it's weird. So, yeah, so your assumptions could also become really abstract really quick too, right? Like, so mass is a really abstract concept. It's a measured quantity in some sense. Now there's electromagnetic equivalents of mass. So basically how hard you have to push on something with a magnet, the same amount of force that you would get from gravity with mass. It's basically, a lot of these concepts just get terminally abstract and people get really, really comfortable with them. But it's a little bit like building a house on sand at some point, because you're not really standing on anything solid if your entire if your entire castle of explanations doesn't terminate in anything physical, then you run into serious problems. I think it's wrapped up too in this thing. I've hit you guys with this word a bunch of times, reification. Have you guys heard of that word? I know I've said it before. Do you know what that word means? Anybody? Somebody remember? Be cool if you guys learned this word. If you learned one new word this semester, I think this would be a good one. Reification. So reification is actually a philosophical fallacy. So it's like philosophers have come up with all these fallacies, which are basically ways that people make arguments that are broken, and they do them all the time. There's all sorts of fallacies of argumentation. And they range. You see them, especially politicians, love fallacious arguments, right? So if you're arguing about some policy and you just start attacking some guy because he has a stupid haircut, like, that's obviously not a logical way to undermine someone's argument, right? His hair has nothing to do with how the state spends its money on healthcare or whatever, right? But we see these in science too, and one of them, my favorite one probably, especially in physics, is called reification. So reification can also be thought of as mistaken concreteness. It's basically where you take an idea, something abstract, and you transform it into a pseudo-physical actor that you can basically apply motion to. So you take the concept of mass, which really can't be understood as anything other than connectivity to your surroundings. It's a concept, right? It's a scalar concept. It scales how connected you are to your surroundings. And then you turn it into a physical object. So now I'm moving this mass around, right? I have a mass and I'm moving it around. What does that mean to have a mass? It's an idea. You can't move ideas around. It makes no sense if I'm like, here, I got some thanks. Can you catch my thanks, right? It's an idea. Thanks is an idea. Love is an idea. Hate is an idea. I can't just be like, can you hold on to my hate for a second? I'll come back for it in a minute. Like, it makes no sense to apply motion to ideas. And so physics in general suffers really, really heavily from, it's really wrought with a lot of reification of this nature. And so Anyways, those are sort of assumption level things that can go off the rails. All right, I think I've gotten completely in a rabbit hole with that. Let's keep going, and these, we'll keep playing with these ideas. They're so important. So remember that one, reification. It's a good one. All right, let's talk about the moon really quick. So does anybody have any questions? I'm not even gonna, I don't even feel like I need to present this, but I probably should, because it'd be really sad if you didn't understand how this works. You guys see the moon all the time. Has anybody not seen the phases of the moon before? It's okay if you haven't. I just don't think it's possible, right? So you guys understand the basic idea behind this? Wish I had like a good way of asking a question that wouldn't throw anybody under the bus for not understanding this. Basically, the way that this works, and this is worth understanding, and actually once you kind of get this picture in your head, you start to just kind of notice it really nicely. So as the sun, particularly as the sun is setting, right, because that's when the moon becomes most contrasted against the night sky. Basically, as the moon is orbiting the Earth, but the Earth is turning really fast, faster than the moon is orbiting. So in order for the moon to make an entire circle around the Earth, it takes about a month, right? And as it does that, it's going to expose more and more of itself to the sun's light, because the sun is essentially coming from one side at all times with respect to where the moon is at. So from where the sun is sitting, the sun's always getting to see every part of the moon, right? But from where we're sitting, the same side of the moon is always facing us. It's basically locked into position with us. It's just tethered right to us. But it does move, and as it moves, its shadow changes. Yeah.
Isn't that called tidal lock?
It is called tidal locking. Yeah. So I want to talk about tides a little bit too as we move forward. But yeah, it's a very similar idea to tides, right? The idea is that actually most of I was about to say all, but I think some of those little dinky moons, especially on Mars and otherwise, are not quite tidally locked. But most moons in our solar system have this thing where they're basically spinning. Their spin is more or less stopped with respect to the bodies that they're orbiting. So they've come into a position where they are essentially, they call it tidal locking, but the reality is that it's just not turning on its own. It's so tightly held by the gravity of the Earth at this point. And the idea is that at some point in its past, it probably was spinning, but that the friction of being held in place gravitationally keeps it from doing that anymore. So anyways, this is the basic pattern that we're left with. You're going to see these phases of the moon depending on where the moon is on any given night with respect to the sunlight during the day. And you can kind of see this. So if you see the sun setting, you'll actually see the moon. You'll see where it is in the sky, and you can start to imagine where it is with respect to its motion around us. Do you guys have any questions about this basic idea here? I don't feel the need to spend a ton of time on it, but I think it would be a terrible shame if you didn't understand this after leaving this class. I know it talks about it a lot in the textbook and stuff, so maybe we won't spend any more time on that. Questions about it? All right, start paying attention to it as you're out there. As you see the moon rise, think about just start thinking about little things like which direction the sun was setting and how it would be casting its light. And you can start to maybe develop a better sense of place, which is pretty cool, like actually understanding how the moon is moving. All right, what else do I want to say? As a result of this, of course, at sunset, the moon's going to be slightly further east every day throughout the course of its cycle, right? And that has to do with the way that it is actually orbiting around us. All right, so you mentioned tides. This is related to tides. I do want to talk about tides, at least briefly, because I think they're quite interesting, and they might teach us about some of the other pieces of this puzzle, including how the Earth manages to have such a nice liquid interior, what keeps it warm. There's a lot of really interesting pieces of this puzzle. So the Earth is, of course, being pulled on by the moon, just like the moon's being pulled on by the Earth. Um, and the outer portion of the Earth is literally being yanked on and changing. Some of the mountains have been measured to be pulled on by the moon up by as much as like dozens of centimeters when the moon passes overhead, which is pretty crazy. But the water, the oceans, are probably the most obvious version of this. So, what happens is that on the side closest to the moon, obviously the water, their oceans, are being tugged towards it. Um, Now, there's also this weird effect where the other side of the ocean is being ejected away from it. You can kind of think about this as like swinging. If the Earth Moon system is like a ball and chain type situation, you can imagine there's kind of a centrifugal force as the water is kind of flung off on the other side. The result is that you get this kind of obloid distribution of the oceans, which is changing as the moon makes its way around. Now, this is a very nice, neat picture. The reality is actually incredibly complex. This is a sort of map of the tides in the actual ocean, and it's quite chaotic because, as you can imagine, uh, the topography, the terrain under the water makes a huge difference on where the tides are filtering and how they're pulled and which pieces are pulled more. So it's actually, what's that? Topography. Thank you. Yeah. Oh, this one's animated. Let's look at that. It's actually quite interesting. Of course, winds and weather and storms play a role. They get a say as well in terms of the way that the water is cycled. Currents, all of these things matter too in terms of the flow of water. So it's not so neat. There are some serious tides, though, that people can predict, which are quite interesting. So every, you know, why would you guys think that there would be bigger tides sometimes than others? There's two reasons I'm thinking of. Yeah.
Well, my first assumption is that the moon is a inksy bit closer to the Earth than before.
There's a bit of that. There's a bit of that. That's close to what I'm thinking, but maybe we can improve on that a little bit. What else is pulling on the Earth?
Some solar tides.
The sun is, exactly, yeah. So there are these moments when the sun and the moon are basically pulling on the Earth in the same direction. So as we'll see, I think I have an animation of this soon. I should have I put it out of order. I'm sorry. I'll come back to that. But basically, the moon doesn't orbit the Earth perfectly in line with the ecliptic, right? It's very close, but it's not quite in line with the path that the Earth takes around the sun. So it's kind of at an angle, which means that um, it actually crosses the ecliptic at 2 points, which are called nodes. And when those nodes are in line with the path of the sun, you have the opportunity every once in a while for and I think this is on the order of decades. You have the opportunity for like these super tides, right, where you have the pull of both the sun and the moon being super strong. So that's kind of interesting. Oh, here's like well, this is an animation. Yeah, so you get mini versions of this a couple times a year. I guess they call them king tides or neap tides. But there's these moments when oh, here we go, where it crosses the orbital plane. So here's the actual orbital path of the moon from the top down, and here you can see it from the side. And you see that it's like a little bit out of plane, if you can imagine that the flat plane of the ecliptic is there otherwise. And you can see that it actually changes and goes from the above the ecliptic to down below the ecliptic. And so it does pass these on the order of some years. Which is really quite beautiful. So it's not this perfect, nice, even orbit that you might expect. And there's some elliptivity to it as well. I think this is exaggerated, but you get kind of a sense of what's going on. So there's these periodic, infrequent, but serious deviations from the tide behavior. Yeah.
Does that mean that, like, during a solar eclipse, the tides might be a little bigger?
Solar eclipse. Solar eclipses are weird. So, see where you're going with that because it does have to be it does have to be crossing in the same path with it. That's a really good question. Maybe you can ask can you ask the internet about that? I'd like to know the answer to that. I don't know. That's a really good question. Yeah, I was about to talk about eclipses anyways. Maybe you can get back to us with that. It's quite interesting. Right. So what else can we say that's interesting? So leading us into eclipses, the Earth, as the moon does this motion, the thought is that, and there's some ways of perhaps approximating this in our own geological record. It seems like the moon is actually slowly moving away from us, which is quite interesting. So they have some records of the tides from the past, and they seem to be less than the pattern that we would have expected had the moon been at the same exact distance that it is to us now. And there seems to be some trend with this. So the idea, in some sense, is that just like our figure skater, when the figure skater has their arms in really close, they're going really fast, right? But in order to conserve that momentum, as it slows down, as the figure skater slows down, the arms come out in order to conserve that momentum, right? And this whole tidal locking, there's friction processes owing to all of this gravity or some frictional analog anyways. And the result is that the moon is moving slowly away. It's on the order of, I think, centimeters per year moving away from us, but it is appreciable. And it is quite far away, actually. Like I've mentioned this at the beginning of the class, but it looks like it's very close when you see it up in the sky. You figured it out?
Well, yeah, it's negligible.
Negligible.
It's a little bit more higher.
The tides?
Yeah, during a solar eclipse than a normal new moon, but it's negligible.
Interesting.
Um,
Yeah, I think it has more to do with those nodal crossing points, which are less frequent when it's like really aligned with the ecliptic.
I
But
always realize when I'm looking at the moon, so I'm like, oh, it looks so close, but it's not that close. 'Cause
it's
you can
really
put
far.
every other planet, including Pluto, between the Earth and the Moon, just line them all right next to each other, and
Yeah,
the moon will still have distance to spare.
it is. It
It's
is
just
pretty unbelievable. Yeah, it is really unbelievable. There's also this. So something kind of another piece of this puzzle which is quite unbelievable. So we should talk about eclipses very quickly. So there's obviously the lunar eclipses, right, where the Earth gets in the path of the full moon's light. But then with the solar eclipses, it's also quite remarkable because there's something particularly beautiful about our position. Speaking about this incredible world that we inhabit, the size of the sun and the size of the moon, apparent angular size, are about the same in the sky. They're very, very close, which is, I would say, almost wholly unique in the solar system. Now, that doesn't mean there's no eclipses on other planets. Like you can see the eclipses on Jupiter. You can see the little shadow crossing across Jupiter. But it's a very different size ratio, right? So the sun's very tiny on Jupiter. If you were standing on Jupiter, if you could stand on Jupiter, I don't think you could stand on Jupiter, but let's say you could. The sun would be very tiny and the moon would be relatively large compared to it. On Earth, they're about the same size, which means we have this beautiful event, right, where you get this perfect little ring of plasma around the outside of it. Did anybody see the total eclipse that came through here recently?
I've
Cool.
seen 2 solar eclipses in my time here.
Heck yeah. Me too. Yeah, I drove down to Austin for the last one, the last total. It was pretty amazing. There was a partial one that was visible up here, but I was under
I
clouds,
always forget
unfortunately.
that it gets cold.
It does. It's very, very strange and really amazing. Um, but that experience that you have if you've seen one of these total eclipses, I think is really there's something very, very strange about it. So, the moon is actually like 400 times smaller than the sun, but it's also 400 times further away from us. Sorry, the sun is also 400 times further away than the moon to us. So it's this perfect match where they really do blot out, they overlap each other almost perfectly. And so if the moon's moving away from us, as it seems to be doing, at some point we won't get quite as, maybe it'll be an even better solar eclipse, I don't know. But yeah, it won't be quite the exact same match that it has been. And in the past, presumably, the sun was blotted out entirely, and we didn't get that nice little annulus around it, which is quite remarkable. So, let's see if these are worth going. So, I'm not sure that we need to look at these. Eclipses have a kind of a really interesting and auspicious history to them too. They've been. Do you guys know the story about Christopher Columbus and the eclipse and everything? So, does anybody know this story?
I do know a different story about the blood moon.
Yeah. I'm trying to make sure I don't mess up the details of this. Um, okay. Well, the rough story is something like, you know, Christopher Columbus is this Spaniard who comes to the Americas, and he's down basically in modern day Haiti, Dominican Republic area, and he's behaving really poorly and so forth with the natives, and basically trying to rip them off and do all sorts of terrible things. And they're on to him actually, and they get really upset. And I think they essentially threaten to, you know, put him to an end, something like that, or some of his men. And he basically had access to an almanac that had records of eclipses, right? Because people in the West had been keeping track of these eclipses. They're actually quite predictable and regular. Um, and he told the chief of this tribe that, you know, you should let my people go. You should let us get back on our ships and go away. Not only that, but you should probably fill up our food rations and give us all of your gold and everything else. Because if you don't, my God's going to come and smite your people. And they were like, yeah, whatever. We don't believe in your God. And he was like, no, like he's going to send a sign. Like tomorrow night, the sun's going to, or tomorrow the sun's going to be blotted out, just as like a sign that you have to do this. And yeah, allegedly it worked. The eclipse came, and yeah,
Was it a solar eclipse or was it that the moon?
I believe it was a solar eclipse.
Okay, because there it says lunar eclipse.
Oh, does it? Okay, then it blotted out the moon. Then hold on one second. I actually have the details written here. Yeah, it was a lunar eclipse. You're right.
Yeah,
So it wasn't.
it's probably like the moon's gonna bleed.
The moon's gonna bleed. Yeah, I bet you that's what it was too. I wish I had the like some of the original chronicles. I was just reading this story on Wikipedia though. Yeah, he said Columbus would said his God would provide a clear sign of his displeasure by making the rising full moon appear inflamed with wrath. Yep, the red moon appeared on schedule, and the indigenous people were impressed and frightened. So there you go. You know, there's you see not the same sort of manipulative stories, but there's really similar stories coming from the Aztecs, from the Mesoamericans too. The Florentine Codex, which is one of the only documents we have from the Mesoamerican people, that the Spanish, when they showed up, they were behaving badly again, and they burned all of the books, more or less. These codexes were kind of like pamphlets, like how maps, when you get them at like the rest stop, they're like folded up into these little. That's how the indigenous Mesoamericans kept all of their records too, in these codices. And the Spanish burned all of them pretty much. They had hundreds of these books, which would have been awesome if we'd had them, because they would have told their entire story of their people. But the Spanish burned them because, I don't know.
That's how you.
That's what people, yeah, that's how you conquer people. Yeah, exactly. But there's this really cool piece. So one of the codices survived. It's called the Florentine Codex. I'll read you a little quote of it. It's kind of interesting. They're talking about a recent eclipse, and it says, when the eclipse came to pass, he, which is the sun deity, turned red, became restless and troubled. He faltered and became very yellow. There was a tumult and disorder. All were disquieted, unnerved, frightened. There was weeping. The common folk raised a cry, lifting their voices, making a great din, calling out, shrieking. There was shouting everywhere. People of light complexion were slain as sacrifices. Captives were killed. All offered their blood. They drew straws through the lobes of their ears, which had been pierced. All in the temples there was singing of fitting chants. There was an uproar. There were war cries, and thus it was said, if the eclipse of the sun is complete, it will be dark forever. The demons of darkness will come down, and they will eat men. So, a very community building experience, I think. Something like that. Um, I don't know. A lot of, especially the Mayans had this very participatory cosmology, right? It wasn't like our cosmology where we're sort of just passengers on a train or something. They were very much believed that they had to make sure that tomorrow came and sort of do their part through all of these ceremonies and so forth. But anyways, eclipses must have just terrified people in general throughout the ages.
Yeah, imagine the sun being blotted out.
Yeah, it must have been totally terrifying. Yeah. So actually, in the West, the idea that it was the moon doing this goes back to like almost 500 BC. This Greek philosopher named Anaxagoras, actually, really brilliant dude. He also was one of the first people to posit that the moon was a rock, that the sun was a burning something or other. Um, but yeah, these are really old ideas, and of course they got completely lost throughout the Dark Ages in the West for 1,000+ years, which is it's very strange how that happens. Um,
And that's what constant war will do to you.
yeah, it's weird. Yeah, the fall of the empire. The Romans didn't really care about scholarship that much, only in so much as like the histories supported their narratives, and it was a very strange post-truth world at the end of Rome. And yeah, you got to be careful about that. It's very interesting. The Greeks, in some sense, made progress that we didn't really revisit again until Enlightenment Europe, which was, of course, after the fall of the religious hegemonies and everything. Strange history on this planet, my friends. All right, so let's talk about the moon itself, though. First of all, questions about eclipses, about tides, about the phases of the moon, any of this stuff that you are obliged to at least have some basic understanding of, having taken an astronomy course. Anything? Yeah.
So with the um like tidal movements with the moon, is that due? Because you also said that because the Earth and the Moon are kind of like pulling on each other, does that like so does that relate to tidal movements? Like is something like under the Earth?
Mhm.
So
Oh, yeah. I
is
didn't even
that
talk about that.
because of that? Is that why the tidal?
Yeah, the tides matter for more than just the water. That's perhaps part of the story too. I didn't even get to mention that. Yeah. Um, so and this ties into sort of the wider, longer geological story of the Earth. Our talk about the Earth got cut a little bit short because, well, we have to make it through so many planets, and we're running out of time. Um, yeah, so one of the huge problems with the geologic history of the Earth is that, and this we're going to see this crop up over and over again. Many of the extant explanations for why does this planet look the way it does, especially with the Rockies, is oh well they used to be more Earth-like or something, but that time has passed for them. They've cooled off, they've lost their atmosphere, whatever. Um, the problem is, under the same regimen, the Earth being approximately the same size as some of these, and really allegedly having the same history as far as how long it's been here in the solar system, it too should have cooled off by now. It has a tremendous amount of residual heat. So the amount of heat inside of the Earth isn't appropriate for how old it is. So I've heard some really interesting. I've actually talked to some different scientists over the years who've tried to address this issue, and some of the more compelling pieces actually do involve the role of the moon in stirring up the innards, basically. So the tides essentially pulling, and that might also, in some sense, have to do with why we have such a stable geomagnetic field too. Because remember, if you think about how we talked about magnetism, we're talking about these eddies, these swirling, almost solenoid-like. Electromagnets inside of under the Earth. How do you keep that churning so nicely? As we're going to see when we look at the Earth's or we look at the Moon's history, you know, the Moon had a magnetic field. It had a much stronger magnetic field at some point than the Earth, as far as we can tell, just by looking at the history of the magnetized rocks in it. Much, much stronger. So what happened, and what's really the difference? I mean, the moon is supposed to have had some sort of liquid, stuff. What do we decide to call it? Magma type innards, just like us. But there's something special about the way that the Earth is being churned, and it might be able to rescue that heat balance as well. So the tides might have some role, some piece of that puzzle to play out at the end of the day. Venus is also very strange. It's like approximately the same size as the Earth. Has no real magnetic field. We're not sure if it ever did have a magnetic field yet, primarily because we haven't really played around on Venus as much as we have on the Earth or the Moon.
Mars.
What's that? Or Mars?
Yeah, because Venus is hell.
Yeah, it's a nightmare. I think the Russians put a satellite down there. It lasted a few minutes. I mean, it's like taking a submarine to the bottom of the ocean, but times 100 or something. It's very, very high pressure, and it's hot, and it's just a terrible, terrible place. There is a mission that NASA is working on to go back there, but it's not gonna last very long. Still, I think that their best bet is to do a bunch of measurements as they descend down to the floor, and hopefully it survives for an hour or two or something like that. But yeah, it's funny how a lot of these space missions end in the destruction of the spacecraft. Like it's just kind of a foregone conclusion. It's a funny way to build a vehicle, that you just destroy it at the end of the journey. Okay. Questions, thoughts? That was a good point. If we had more time, we could investigate that further. But I think we'll start to look at the differences in these, especially the magnetism. I mean, that's something that's really, really special about this place. And it's not fully understood what makes us special. I mean, Venus doesn't have a moon, so that might be an interesting piece of the puzzle. It's a very unique situation we have here. All right. Let's think about the moon as a rock, as a celestial body. Yeah.
I think it might be nice to point out that it has a name.
Oh, Luna.
Yeah,
Yes,
Never-
you're big on giving her proper name.
that's where lunar comes from,
Yep.
obviously. But yeah,
Yeah. I mean, is it Greek? Is it Latin?
I believe it's Latin.
Latin. Luna. Yeah. Yeah. Technically, the Earth is Terra or Telea, depending on Greek or Latin. So we do have names, but Earth and the Moon should suffice. Generally, the is good enough. The is, by the way, a very, very interesting. Oh God, I'll get off on. My wife is Russian. They don't have the in Russian, which is quite interesting, actually. And it's interesting how useful these definite articles actually are. But anyways,
English is a good language.
I think it's deeper than that, actually. I think it's yeah. We'll talk about it after class if you want. It's a whole other issue. I think it has roots in sort of the divination of certain definite objects over general classes, and the Russians are sort of very godless people. All right, no, for real, it's a very different approach to reality than we have in the West. I love the Russians, though. They have incredible literature. All right. Let's talk about the natural history of this thing. So, like I said, this dude Anaxagoras wrote a bunch of cool stuff about the moon that was pretty on point and correct. He also understood the sun better than anybody for the next 2,000 years, pretty much. But after that, it was kind of crickets. That there was let's see, the Indians, halfway through the first millennium, were the first people to understand that the moon didn't actually, well, not the first since the Greeks to understand that the moon didn't glow of its own accord. So people generally thought that the moon emitted light. So these Indian astronomers actually were the first to recognize that it was actually reflected light from the sun, which is actually a huge step in the right direction if you want to understand the phases of the moon like we did at the beginning. Um, what else? Yeah, pretty much crickets for the next 1,000 years or so. Now, as soon as Galileo got a hold of that telescope, he started making these drawings of the moon, and this was the first time that people really, by and large, were persuaded of the moon as rock idea. You could start to see the mountains, the craters for the first time. Later, a little bit later, I think this was towards the end of that same century in the 1600s, this dude, Robert Hooke, one of my favorite scientists of all time, came along. Um, it's kind of amazing. Well, anyways, Hooke made these incredible drawings, really high resolution drawings. He also was one of the first people to get a hold of a microscope, and he did these incredible drawings of the hairs on the back of fruit flies, and just an incredible dude. And when he wasn't doing all of that, he basically invented elastic mechanics. So yeah, people were just special back then. Um, what else? It actually took until about the 1800s for people to conclude that there wasn't actually water on the moon. Um, because if you look at the moon, it actually has a bunch of dark spots. They were originally named mare, which is essentially means sea in Latin. So people thought there was oceans on the moon, which is pretty reasonable, honestly. By contrast, and we'll get back to this when we deal with Mars, but people thought that there were forests on Mars until the 1970s. So, you know, this worldview we've all inherited today, where we understand all of the planets are kind of lifeless and dead, that wasn't the norm until very recently. Um, so Mars has this sort of seasonal pattern where there's condensation of different gases, and it changes the appearance, so there is a darkening of Mars. We'll deal with that when we get to it. But yeah, people were pretty convinced there was life on Mars until they went there in the 70s. All right, so our moon. Let's talk about this thing a little bit. Um, you know, what is and this kind of calls into an interesting question about moons in general. Like, what is a moon? What makes a moon and not a planet? What makes a planet and not an asteroid? Yeah.
Uh, a moon orbits a planet,
And what else?
and it doesn't draw in objects of moon size.
Yeah, right. It's like it basically means it doesn't get orbited by anybody else. I think that's a good definition. So moon orbits somebody. It doesn't get orbited by anybody else. And there's a couple other things we could say. Like I mentioned the tidal locking. For the most part, all the moons that we're aware of are tidally locked, except for some of the like little potato dirt ball things. Yeah.
Have we ever found a moon orbiting the moon of another planet?
Orbiting a moon. I don't think so. No, but we also can hardly see huge planets in other solar systems. So who knows, right? I mean, it brings into an interesting question. So, like, Venus is tidally locked to the sun. Venus has no other moons orbiting it. So is Venus the sun's moon?
No, because the sun isn't a planet.
Yeah. So what's a planet? What defines a planet? This is kind of interesting.
Star.
Not a star. Well, we'll play with that in a little bit. But let's go with that. So, but in terms of things that are not stars, what makes it a planet versus, I don't know, an asteroid or something?
It's big and round.
Round, actually, that's what it is. That seems like that's the thing. So the way that it's generally defined, first of all, it has to orbit a star. So I guess that takes Venus off the list. But the other qualification is that it has this sufficient amount of material that it self-gravitates into this round shape, basically. So it has to pull on itself hard enough to get into a ball. Uh, but even this is really challenging because there's these asteroids, right? Ceres in particular, which is weird because it's only 600 something miles across. It has not even close to the amount of atoms to be able to pull itself into a ball, but it's still a ball, and nobody knows why. It's very, very interesting and strange. And this is out in the asteroid belt. And of course, all of the asteroids are also orbiting the sun, right? So this thing's orbiting the sun. It's round. Is it a planet? It's too little. I don't know. Yeah.
What's Pluto's uh not moon, but its other It's two. It's not a moon, but they're orbiting each other.
Yeah, Charon, and what's the other one? Yeah. We'll get to Pluto eventually. But yeah. So, anyways, these definitions are just kind of strange at some points. This is a wonderful mystery. We'll talk about the asteroid belt in brief, but the asteroid belt's very, very strange. Explanations for it. I'll save that for later. But for now, rounded bodies that are essentially in this what we would call a hydrostatic equilibrium. They're essentially not flying apart. They have sufficient gravity to round them, and they orbit a star. So that's what a planet is. So the moon isn't like that. It's obviously orbiting us. This is the kind of model that we have of the moon at this point. Some of this is done from actual sensors, so very in terms of like getting an idea of what's going on inside of it. Some of it's done from very similar seismic studies that we did with the Earth. Do you remember when we were talking about this Danish geophysicist who came up with these ways of refracting sound essentially through the Earth and getting the different density layers, right, or stiffness layers of the Earth? Same thing with different sensor studies on the moon. And then also by looking at how much gravity it has, looking how big it is, you can essentially assess its density and you can make up models. You're trying to solve the problem of what it's made out of. And the most thing that's interesting is that you conclude that while it might have a solid inner core, it doesn't have a really good iron core like us, which is quite interesting. So people over the years, and by over the years, I really just mean in the last few minutes of geological time, since people have been considering mechanistic explanations for what the heck this thing is. Remember, people, right? They just in the 1600s decided that it was a rock in the sky for the first time. So we've been doing this for almost no time. There's been a few different ideas about where this thing came from. So one of the first ideas was that the Earth just scooped it up. Right? It looks nothing like the Earth. It looks nothing like any of the planets around us. It must have come from somewhere else, and we just grabbed it as it went by. Now, as the mathematicians started cranking on that idea, they realized that in order to pull that off, you'd need something to slow it down as it was going by. And nobody could figure out what happened to the thing that slowed it down. In other words, there should be another body that slowed it down as it went by so that it could stop and get pulled into orbit with us, right? That didn't work out. So this theory, nobody could solve that problem. Maybe true, but it became less interesting. Then they tried on another model where they were like, well, maybe the Earth and the Moon were originally one chunk of stuff, and since the Earth was spinning really fast when it was first formed, it sort of ripped itself apart, like a fission model, right? Now, there's problems with that as well, right? Because if it was from the same goop and split itself apart, you'd have a hard time explaining some of the different features of it, particularly the water abundance, right? So I don't know if you guys remember, we're talking about the Earth, and I was like, there's a lot of water underneath our feet, and it's not liquid, right? It's just bound up in the rocks and these hydrated minerals, right? Lots, like maybe 6 or 7 oceans worth of water, technically, just in the rocks. The moon doesn't have much of that. It does have a little bit, but almost none compared to us in terms of its hydration, which is really, really weird if they both broke off from the same hunk of stuff. So people moved on from that model. They needed a way to figure out how the moon got all of its water baked out of it. And then, again, the next idea was kind of similar, but it was like, well, the moon formed at the same time as the Earth in the same place that it's at more or less right now, maybe a little closer, out of the same pile of building blocks. But again, you still run into the same problem. If there's all this stuff there, the Earth has a very different composition, particularly with respect to the water. Why does the moon not have that? That brings us up to today, where the most popular idea now is that there was 2 planets in the early solar system, the Earth and this other planet called Theia, and they were on sort of overlapping orbits. And one day, Actually, I got a picture of this, so I'll just play the picture while I tell the story. It's a lot more fun to look at it if I can get it to go. So one day, of course, these are supposed to be in the early days of the solar system, which was a mere few billion years ago in this rendition of the story. The thing basically comes by and smacks into the side of the Earth, which hits it at just the right angle that it basically rips off a blob of the mantle of the Earth and takes it off. So it doesn't get any of that iron from our core, I guess. I guess the Earth absorbed most of the iron or something from the Theia. And the moon, there was just kind of a big mess that resulted after this. I think this animation has, well, let's see where it goes. Let's watch it for a second. Make sure that I get this right. So there's a bunch of debris that's flown out into, near Earth orbit, and it sort of swirls around. You can imagine kind of a Saturn-like ring of debris that comes out of this. And then the moon kind of congeals. Actually, the latest simulations of this, well, first of all, simulations are very difficult to make them work out. The ones that that I've seen lately have the moon forming in a matter of days, something really, really fast. It's unbelievable, actually. So here we go. Is this still the Earth we're looking at? Yeah, I guess so. Play this on 2x. Now, I guess while this is playing, I'll pick on it a little bit. So, in some sense, this still has the same problem with the water that we had before. That the moon does have water, but it doesn't have water in the mantle in the same way that the Earth has water in the mantle. Now, the actual elements are really, really similar. Like the silicates, the basalt, it's all very, very similar to the Earth in some sense. But it's obviously very, very different looking at the end of the day. Even allegedly in this model at the beginning of it, you have very, very different ratios. So and it's not just the water too. There's also iron oxides and some other elements that just don't line up with what we would expect from the thing being formed from the mantle. If it didn't form from the mantle, why doesn't it have any iron in the core? This is very strange too. It's also very, any of these models have to explain how it is that there's so much angular momentum in this system. So the thing is spinning. The Earth-Moon system is spinning really tightly as a single unit. You would think that as these things collided, that you would actually bleed out a lot of that rotation. In other words, you would kind of, as they smash into each other at the angle given in these simulations, that the two things would kind of slow down in some sense. The spin would actually be a lot less. However, the spin, given the origin story for the Earth itself, which we barely touched on, but I think your textbook cleans it up quite nicely, has to do with this spinning ball that's essentially slowing down over time. This angular momentum issue still rears its head up. The last piece is the rarity and uniqueness question. So if this is how the moon formed, why is it that we don't see the other terrestrial planets having moons like this? So if it's quite common in the early solar system for different rocky planets to smash into each other and make moons, why doesn't Venus have a moon like this? Why doesn't Mars have a moon like this? Mars has these tiny little dirty rock pile things that are like, tiny compared to, they're not in any way appreciable. So why hasn't this happened? So all of these theories are tricky. They're very difficult. I of course would go and add another possibility to this, which is that perhaps the universe isn't 14 billion years old. Perhaps the universe is trillions and trillions of years old. And perhaps the moon is extremely, extremely old. And perhaps really rare things do happen in the early, assembly of this solar system. I remember, I think I've mentioned this in this class, but I have an acquaintance who's an astronomer in France, and he runs these simulations where he's always trying these like outlandish situations. Could the Earth could the solar system pick up a new planet? What would it take? And he always concludes like, yeah, it's doable. Like I can always find a simulation that will have the Earth grab a moon up, or I can have the solar system grab a planet up. But it's extremely improbable, and you'd have to have another solar system going by at the exact same moment, or this planet that's being interacted with, a free-floating planet coming by at the exact right moment. So they're extremely improbable. But given a really long time, improbable things actually become quite regular and normal. That's the strange piece of the puzzle of having our cosmology bound the timelines for which we can tell these stories. Let me bring up a couple more pieces before we close down on this. So when we look at the surface of the moon, it's also quite strange and kind of raises more questions than answers. So one thing that's quite obvious is that it's super beat up with craters, right? Now, some of it isn't beat up with craters. There's these big mare things, the things that people thought were oceans originally, right? So we're looking at the back side of the moon from us here. This is the front side that you can see at night.
I always think it's funny we call the dark side of the dark side.
I know. Yeah, that's another thing you can say you learned in astronomy class. There is no dark side of the moon. Somebody tell Roger Waters. All right. So what's up with these mare, and what's up with these cratered pieces? Now, it's quite obvious that the mare don't have hardly any craters compared to the rest of the moon. Now you might think, okay, well that's fine. I mean, the mare must have been formed relatively recently, right? But the standard story for the way that the moon came to have the surface that it has is actually that there was these huge impacts. There's this moment we've talked about in the past called the late heavy bombardment. Do you guys remember why we talked about this before? With the oceans?
There's a theory that the heavy bombardment had comets that brought water to
Right. Exactly. So the most popular theory, at least when I was a kid, when I was taking astronomy class, was that the oceans came from comets, from this period in the early moments of the solar system's formation, where the water was being delivered by comets, which is pretty far out. I had a hard time with it when I was a little kid. Still have a hard time with it. But I think people have been moving more away from that as they're finding these hydrated minerals underneath the ground and coming up with chemical explanations for the. But anyways, they're still holding on to this late heavy bombardment idea. So the idea was that the moon was getting beat really hard with all these asteroids in the early days of the solar system. Some of them formed these huge basins. These basins sort of thinned the crust such that the underlying magma, I always want to say lava, magma was able to well up and form these big lava lakes because they're on the surface, right? So the idea was that all of this bombarding with all of these craters, it all actually happened, geologically speaking, one day in the past. Yeah.
I guess I should point out lava and magma are materially different
Okay.
because magma is significantly denser. It's a different if
Because it's underground.
yeah, if you have magma and it cools, you won't have volcanic igneous rock. It won't. I mean, it's kind of, but it's not the same type of rock.
Okay.
Because it's too. I forget if it was just too heavy or dense to have gone up, but lava is just less dense.
More aerated, perhaps?
Maybe.
Yeah.
Sure.
I don't know.
I just know it's less dense.
All right, we'll look into this. My point that I'm trying to paint a picture for you of here is that those mare, particularly the basins that allowed for the formation of these lava fields that became the darkened spots, they're basically like basalt, right? Those are all supposed to have formed at the same time as this cratering system. So, this is weird because if we look at the cratering of the Earth, if we look at the cratering of the moon, the rate at which we see craters forming on the moon, and we try to project that to give the moon a date, right? How old is the moon based on how often it gets hit with stuff? Well, the reality is that the moon would be tens of billions of years old because it doesn't get hit with asteroids hardly ever. So the only way that we can make all of those asteroids appear on the moon in our story is if they all happened, in one moment, basically, in the deep past. So this is another piece of the story of the appearance of the moon that I think it doesn't sit very well with me. I don't know. How does that sit with you? Maybe it sits with you fine. Yeah.
Um, I think like I don't know. It depends because like the concept of there being a heavy bombardment period does make sense given given the way the asteroid belt formed and moved away basically. Um, I guess, but
Yeah, I'm not sure that the asteroid belt is involved in the heavy bombardment, actually. We'll get to the asteroid belt, though. I mean, look, I guess I don't want to bury the lead here too much. The point is that these mare were supposed to have formed more or less on, in some proximity to the formation of these crater highlands. Mare are lower as well, right? Mare have far less craters on them. So in order to tell the story of how the moon came to have gazillions of craters all over it, it has to be done in a really short amount of time. Otherwise, the moon exceeds the age of the universe by several, let's say 4 or 5 times the age of the universe, if we consider it to have a linear trajectory of being bashed by things. And it's not alone. So there's a number of bodies in the solar system that look like the moon. We'll be checking out some of them as we go forward. The Mercury is one of my favorites. It's actually quite a bit like the moon in many ways. And again, if you try to have this be a linear evolution where it's accumulating asteroid strikes at a regular pattern, you end up with a very, 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 very old moon. So it's just an interesting mystery. I find this standard explanation to be a bit unsatisfying, but again, it's not like anybody can go back 3-4 billion years and see what happened. We have to tell stories about what happened. Yeah.
uh, when you brought up that the lava, like those lavas, like the first thought might be that they were young, right?
With the mares?
Yeah, Mars, but the standard explanation says they're not. My mind jumps to it's the part of the moon that's always facing the Earth, and so it's the part facing having the most gravity, like pull from the Earth comparatively. So my initial assumption is, well,
What?
maybe that affected lava rising up from within the planet, but also that probably doesn't make that much sense.
Yeah, I looked into that one. I found that there was some problem with that. I'd have to go back and read about it some more.
There being massive meteors that would have somehow missed.
That's the very strange piece of it, right? So the mares are only on. So what Dante is saying is the mares are on the side facing us, which is very strange if the basins that led to the thinning of the crust, the moon's crust, to give rise to those lava lakes. Those basins were formed by giant impacts in the standard story, right? But why in the world would the side closest to us, which is presumably better shielded, be smashed with these giant things and not the other side, which would probably be more exposed? It's very strange. I really don't. I don't know. I don't think this story's done. Is all I'm saying. I don't. I'm not telling you I know what the story is necessarily, but the moon looks extremely old. I will tell you that much. I wouldn't be surprised at all that if our cosmological horizon gets bigger, that the moon's story gets longer, and most of the stories of all the planets in our solar system get longer. I don't want to keep you guys late. Let's think about this, and I want to get your thoughts more. Drink some coffee before coming to class next time. I really want to talk to you guys. It's so boring for me otherwise. But otherwise, I hope you guys have a good week. I'll see you on Thursday.